Hello there, and welcome to The Sleepy Astronaut, where the universe unfolds its secrets and starlight guides us gently through the mysteries of space. Tonight's celestial journey takes us to one of the most extraordinary discoveries ever made by the James Webb Space Telescope, a finding so unexpected it has astronomers scratching their heads and rewriting textbooks. We're talking about sleeping beauty galaxies, dormant cosmic giants that have been caught napping in the early universe. And before we drift into this cosmic slumber party, I'd love to know where in the world you're watching from and what time it is where you are. Fitting, isn't it? A video about sleeping galaxies, and here we are, scattered across time zones, each finding our own moment of wonder beneath the same starlit sky. If you find this voyage through space and time soothing, enlightening, or just a lovely way to unwind after a long day, I'd be ever so grateful if you gave the video a like and maybe subscribed. It helps this little corner of cosmic calm reach others who might need a peaceful pause among the stars. Now, I do hope this isn't so fascinating that it keeps you awake, but if it does, well, at least you'll have learned something remarkable about the universe before you drift off. So settle in, slow your thoughts, and let's begin. Because somewhere between the first light of creation and the gentle hum of distant worlds lies a story that changes everything we thought we knew about how galaxies grow up. Imagine, if you will, waking up one morning to find that your garden had suddenly stopped growing, not because winter had come or because you'd forgotten to water it, but simply because it had decided to take a cosmic nap. That's essentially what astronomers discovered when they pointed the James Webb Space Telescope toward the distant universe, expecting to find galaxies blazing with the fury of stellar birth. Instead, they found something utterly bewildering: galaxies that had simply switched off their star-making factories and gone to sleep. These aren't just any galaxies, mind you. These are ancient cosmic structures that existed when the universe was barely 1 billion years old, a time when by all rights they should have been the most active star-forming regions in all of creation. It's like finding a bustling city that suddenly decided to close every factory, every workshop, every creative endeavour, and just rest for a while. Astronomers have given these mysterious objects a rather poetic name: Sleeping Beauty Galaxies. And the name couldn't be more fitting because, just like the fairy tale princess, these galaxies appear to be in a deep slumber, waiting perhaps for some cosmic prince to wake them up. But here's where the story gets even more intriguing. These sleeping beauties aren't rare cosmic oddities tucked away in forgotten corners of the universe. The James Webb Space Telescope has now identified 14 of these dormant giants, each one challenging our fundamental understanding of how galaxies evolve and grow. Some of these cosmic sleepers are relatively modest affairs with masses around 40 million times that of our Sun. Others are absolute monsters, tipping the scales at 30 billion solar masses. That's like comparing a cosy cottage to a sprawling metropolitan city. Yet both have decided to take the same cosmic nap. To understand just how remarkable this discovery is, we need to journey back to the early universe, a time when everything was different. The cosmos was smaller, denser, and filled with the raw materials needed to build stars and galaxies in abundance. It was a time of cosmic youth when the universe was only 10% of its current age, and everything should have been happening at breakneck speed. Star formation should have been explosive, continuous, and relentless. After all, there was no shortage of coal gas, the essential ingredient for making new stars, and the gravitational forces pulling everything together were stronger than they are today. Yet somehow these 14 galaxies had managed to hit the pause button on their stellar assembly lines. The discovery came as such a shock that astronomers initially wondered if their instruments were malfunctioning. How could galaxies in the early universe possibly be dormant? It violated everything we thought we knew about cosmic evolution. It would be like finding a teenager who had decided to stop growing, not because of any external force, but simply because they felt like taking a break. The technical details of how astronomers made this discovery are as fascinating as the discovery itself. The James Webb Space Telescope, with its unprecedented ability to peer into the infrared spectrum, can see light that has been stretched by the expansion of the universe light that left these galaxies when they were young and active, but had been redshifted into wavelengths invisible to earlier telescopes like Hubble. By analysing the spectroscopic fingerprints of this ancient light, astronomers could determine not just how far away these galaxies were, but also what they were doing, or more precisely, what they weren't doing. When light passes through the outer layers of stars and the gas surrounding them, it picks up chemical signatures, specific wavelengths that tell us about temperature composition. And most importantly, for this story, the rate of star formation. Active star-forming galaxies have a particular spectroscopic signature. They're bright in certain wavelengths and show the telltale signs of hot young stars and glowing gas clouds. But these Sleeping Beauty galaxies showed something entirely different. Their spectra revealed the presence of older, cooler stars and a complete absence of the signatures associated with active star formation. It's a bit like being a detective at a crime scene where all the evidence points to something that should be impossible. The spectroscopic data was clear and unambiguous. These galaxies had been actively forming stars at some point in their history, but then sometime between 10 and 25 million years before the James Webb Telescope observed them, they had simply stopped. The stellar nurseries had closed down, the cosmic construction sites had been abandoned, and the galaxies had entered a phase of dormancy that astronomers are still struggling to understand. What makes this discovery even more remarkable is the sheer diversity of these Sleeping Beauties. They're not all the same type of galaxy, taking the same type of nap. Some are relatively small and modest. Others are massive beyond imagination. Some appear to have been dormant for just 10 million years, a mere blink of an eye in cosmic terms, while others had been sleeping for 25 million years or more. This diversity suggests that whatever mechanism is causing these galaxies to go dormant, it's not limited to specific types of cosmic environments or particular galaxy masses. The implications of this discovery ripple through our understanding of cosmic evolution like waves in a still pond. If galaxies can simply switch off their star formation in the early universe when conditions should be perfect for stellar birth, then we need to completely rethink our models of how the universe evolved from its primordial state to the rich tapestry of galaxies. We see today it's not just a minor adjustment to our theories, it's a fundamental challenge to the way we think about cosmic growth and development. Consider for a moment what this means for our understanding of the early universe. We've always assumed that the first billion years after the Big Bang were a time of relentless activity, when matter was condensing into the first stars, and galaxies were growing rapidly through continuous star formation. But if some galaxies could take extended breaks during this crucial period, then the history of cosmic evolution is far more complex and interesting than we ever imagined. The Sleeping Beauty galaxies also raise profound questions about the nature of galaxy evolution itself. We've long thought of galaxies as relatively steady systems that grow through continuous accretion of gas and steady star formation, punctuated perhaps by occasional mergers with other galaxies. But these discoveries suggest that galaxies might be more like living organisms that go through phases of activity and rest periods of growth and dormancy cycles that we're only just beginning to understand. What's particularly intriguing is that these dormant phases appear to be temporary. The research suggests that most of these sleeping galaxies will eventually wake up and resume their star formation activities like cosmic hibernation that serves some deeper evolutionary purpose we don't yet comprehend. It's as if the universe has built in rest periods for its most important structures, allowing them to pause, recharge, and perhaps prepare for future phases of growth and development. The discovery of Sleeping Beauty galaxies also highlights just how much we still don't know about the cosmos. Despite decades of astronomical observations and increasingly sophisticated theoretical models, the universe continues to surprise us with phenomena that challenge our most basic assumptions about how things work. These dormant galaxies are a humbling reminder that the cosmos is far stranger and more wonderful than we ever imagined. As we delve deeper into this cosmic mystery in the coming parts of our journey, we'll explore the possible mechanisms that could cause such massive structures to simply switch off their star-making abilities. We'll investigate the role of supermassive black holes, cosmic feedback processes, and the complex dance of gas and gravity that shapes galactic evolution. We'll also discover how these sleeping beauties might eventually wake up and what their slumber tells us about the future of star formation in our universe. But before we can understand how these cosmic sleeping beauties might eventually stir from their slumber, we need to explore the fascinating mechanisms that could cause such enormous structures to simply switch off in the first place. Imagine, if you will, the delicate balance required to keep a galaxy actively forming stars. It's rather like maintaining a perfect garden where everything must be just right. The temperature, the nutrients, the timing, and the environment all working in harmony to sustain continuous growth. At the heart of every galaxy lies a complex ecosystem of gas dust and gravity where cold molecular clouds slowly collapse under their own weight to birth new generations of stars. This process requires a steady supply of cool gas, the raw material from which stars are born, and in the early universe this gas was abundant everywhere. You looked, the cosmos was like a vast cosmic pantry stocked with all the ingredients needed for stellar cuisine. Yet somehow these sleeping beauty galaxies had managed to empty their pantries, or perhaps more accurately, something had come along and cleared the shelves. The leading suspect in this cosmic mystery is none other than the supermassive black hole that lurks at the center of nearly every galaxy. These gravitational monsters, millions or billions of times more massive than our sun, are not the quiet, dormant objects you might imagine. Instead, they can become the most powerful engines in the universe, capable of outshining entire galaxies when they feed on surrounding matter. But here's the twist: while black holes are famous for consuming everything that comes too close, they can also become cosmic bulldozers that push material away from their host galaxies. When matter spirals into a supermassive black hole, it doesn't simply disappear quietly into the void. Instead, it forms what astronomers call an accretion disk, a swirling maelstrom of superheated gas that glows brighter than 1 trillion stars. As this material inches closer to the point of no return, it releases tremendous amounts of energy in the form of radiation and powerful jets that can extend for hundreds of thousands of light years beyond the galaxy. Itself, these jets act like cosmic fire hoses, blasting away the very gas that the galaxy needs to form new stars. Picture, if you will, a cosmic gardener who, instead of watering the plants, decides to turn the hose on full blast and wash away all the soil. That's essentially what an active supermassive black hole can do to its host galaxy. It heats up the surrounding gas to temperatures so extreme that it can no longer cool down and collapse to form stars. Or it simply blasts the gas clear out of the galaxy, altogether leaving behind a barren cosmic desert where once there were fertile stellar nurseries. But black holes aren't the only culprits in this cosmic crime scene. There's another suspect equally capable of shutting down star formation, and it comes from the very stars themselves in a process that astronomers rather poetically call stellar feedback. Imagine a galaxy as a bustling factory where new stars are being manufactured on a cosmic assembly line. But unlike earthly factories, these stellar workshops produce some rather explosive byproducts. When massive stars reach the end of their brief but brilliant lives, they don't simply fade away quietly. Instead, they explode as supernovae with the force of billions of nuclear weapons detonating simultaneously. These cosmic explosions release tremendous amounts of energy that can heat and disperse the surrounding gas, creating vast bubbles of hot material that expand outward like cosmic soap bubbles. But instead of being delicate and ephemeral, these bubbles are driven by forces so powerful they can sweep away entire regions of star-forming gas. The process doesn't stop there. Massive stars also produce intense stellar winds, streams of charged particles that flow outward at speeds of thousands of kilometers per second. These winds, combined with the radiation pressure from the bright young stars themselves, can act like a cosmic leaf blower, pushing away the very material needed to form the next generation of stars. It's a fascinating example of cosmic self-regulation, where the process of star formation itself can shut down future star formation. What makes this stellar feedback mechanism particularly intriguing is its timing. Massive stars live fast and die young, typically exploding as supernovae within just a few million years of their birth. This creates a natural delay between when stars form and when their feedback effects kick in. During this delay period, a galaxy can go through a burst of intense star formation, creating many massive stars in a relatively short time. But once these stars begin exploding, the cumulative effect of their combined feedback can be so powerful that it shuts down star formation across the entire galaxy. This leads us to a remarkable concept that astronomers call bursty star formation. Instead of the steady, continuous process, we once imagined galaxies in the early universe appear to go through cycles of intense activity, followed by periods of relative quiet like cosmic heartbeats that pulse with the rhythm of stellar birth and death. These bursts can be incredibly dramatic, with galaxies forming stars at rates hundreds of times faster than our own Milky Way, only to suddenly fall silent for millions of years. The timing of these bursts and quiet periods depends on a delicate balance between the rate at which gas falls into the galaxy and the rate at which stellar feedback pushes it away in smaller galaxies with weaker gravitational fields. The feedback from supernovae and stellar winds can be particularly effective at expelling gas, causing longer periods of dormancy. But in larger, more massive galaxies, the stronger gravity can hold onto the gas more effectively, leading to shorter, quiet periods and more frequent bursts of activity. There's also the fascinating possibility that these Sleeping Beauty galaxies are experiencing what astronomers call galactic interactions. Imagine two cosmic dancers waltzing through space, occasionally coming close enough to gravitationally influence each other. When galaxies approach one another, their mutual gravitational attraction can distort their shapes, stretch out long tidal tails, and most importantly, for our story, strip away the gas needed for star formation. These galactic encounters don't necessarily result in dramatic collisions. Sometimes they're more like cosmic near misses, where galaxies pass close enough to disturb each other's gas reservoirs, but not close enough to merge completely. The gravitational tides raised by such encounters can heat up the gas, making it more difficult to form stars, or even eject it from the galaxy entirely, leaving behind a dormant system that may remain quiet until new gas can be acquired from the surrounding cosmic environment. The process of gas heating and cooling plays a crucial role in determining whether a galaxy remains active or falls into dormancy in the early universe. The cosmic microwave background radiation left over from the Big Bang provided a minimum temperature below which gas could not cool. This radiation was much more intense in the early universe, potentially making it more difficult for gas to cool and collapse into stars, particularly in smaller galaxies that were already struggling against stellar feedback. But perhaps most intriguingly, these various mechanisms don't work in isolation. Instead, they can reinforce each other in complex feedback loops that amplify their individual effects. A supermassive black hole might begin expelling gas from a galaxy, making it easier for stellar feedback to clear out the remaining material. Or a galactic encounter might compress gas, leading to a burst of star formation that produces so many massive stars that their combined feedback shuts down the galaxy more effectively than any single mechanism could manage alone. The temporary nature of these dormant phases adds another layer of complexity to the story, unlike the permanent quenching that occurs in massive galaxies. Today, these early sleeping beauties appear to be taking cosmic power naps that last anywhere from 10 to 25 million years, a significant period by human standards, but barely a moment in the billions of years of galactic evolution. This suggests that the mechanisms causing the dormancy are not permanently removing the gas from these galaxies, but rather temporarily making it unavailable for star formation. Over time, the expelled gas can cool down and fall back into the galaxy. The heated gas can gradually return to temperatures where it can once again collapse to form stars, and even new gas can be accreted from the surrounding cosmic web, like cosmic rainfall, that slowly refills the galaxy's reservoirs. This cyclical process of dormancy and reawakening gives these galaxies a rhythm all their own, a cosmic breathing pattern that we're only just beginning to understand. What emerges from this intricate cosmic dance is a picture of galaxy evolution that's far more dynamic and unpredictable than we ever imagined. These Sleeping Beauty galaxies aren't following the steady, predictable growth patterns that our computer simulations once suggested. Instead, they're living, breathing entities that pulse with their own internal rhythms, sometimes racing ahead with furious bursts of stellar creation, and sometimes pausing to rest like cosmic creatures that need time to digest their stellar meals before continuing their feast. The discovery has sent ripples through the astronomical community because it challenges one of our most fundamental assumptions about the early universe. We've long believed that the first billion years after the Big Bang were a time of relentless cosmic construction when every available bit of matter was being rapidly assembled into the first generation of stars and galaxies. It was supposed to be the universe's most productive period, a time when efficiency was at its peak and waste was minimal. Yet here we have evidence that even during this cosmic rush hour, some galaxies were taking extended coffee breaks. This revelation forces us to reconsider the very timeline of cosmic evolution. If galaxies could afford to take million-year sabbaticals during the universe's most formative period, then perhaps the early cosmos was even richer in resources than we realized, or perhaps the processes governing galaxy formation are more sophisticated and self-regulating than our models account for. It's like discovering that the most successful companies in history actually improved their performance by scheduling regular periods of complete inactivity. The implications ripple outward through every aspect of our understanding. Consider the chemical enrichment of the universe. Every generation of stars that forms and dies adds heavy elements to the cosmic mix. Carbon, oxygen, silicon, iron, all the ingredients necessary for planets and ultimately life itself. If galaxies are taking regular breaks from star formation, then the pace at which the universe becomes chemically enriched is more irregular and complex than we thought. Some regions might experience rapid enrichment during active periods, followed by chemical stagnation during dormant phases. This bursty, irregular pattern of star formation also affects how we interpret observations of the distant universe. When we look at galaxies, billions of light years away, we're seeing them as they were billions of years ago, but we're only getting a snapshot, a single moment frozen in cosmic time. If we happen to observe a galaxy during one of its active bursts, we might conclude it's a powerhouse of star formation. But if we catch it during a quiet period, we might dismiss it as a cosmic underachiever. The reality is that both observations could be correct, just captured at different points in the galaxy's natural cycle. The Sleeping Beauty galaxies also shed new light on the mysterious process of galaxy mass assembly. How do galaxies grow to become the massive structures we see today? If they're periodically shutting down their star formation factories, the answer appears to lie in the cumulative effect of multiple bursts over cosmic time, like a savings account that grows through irregular but substantial deposits, rather than steady monthly contributions. Each burst adds a significant amount of stellar mass to the galaxy, and even though there are quiet periods in between, the overall trend is still upward growth. What's particularly fascinating is how these dormant periods might actually benefit the galaxies in the long run. During active star formation periods, galaxies can become quite chaotic with supernovae explosions, stellar winds, and intense radiation, creating turbulent environments that make it difficult to form stars efficiently. But during quiet periods, the galaxy can settle down. The gas can cool and organize itself, and conditions can become more favorable for the next burst of activity. It's like allowing a busy kitchen to cool down and reset between service periods. The role of supermassive black holes in this process adds another layer of intrigue. These cosmic monsters aren't just passive participants in galactic evolution, they're active agents that can dramatically influence their host galaxy's behavior. But here's the fascinating paradox. The same black hole activity that can shut down star formation by blasting away gas can also trigger it by compressing gas in certain regions, creating a complex push and pull dynamic that varies over time. Recent observations have revealed galaxies where the central black hole appears to be simultaneously destroying star formation in some regions while triggering it in others, creating a patchwork of activity and dormancy across the galaxy. It's like having a cosmic conductor who can make different sections of the galactic orchestra play at different times, creating a symphony of stellar birth and death that unfolds over millions of years. The discovery of these sleeping beauties has also revolutionized our understanding of how galaxies interact with their environments. We used to think of galaxies as relatively isolated systems that evolved primarily through internal processes. But these observations suggest that external factors play a much more important role than we realized. The cosmic web of dark matter filaments that connect galaxies can channel gas toward or away from them. Neighboring galaxies can strip away star-forming material, and even the background radiation from other cosmic sources can influence whether gas can cool and collapse. This environmental sensitivity means that identical galaxies placed in different cosmic neighborhoods might evolve along completely different paths. One might become a prolific star former, while another might spend most of its early life in dormancy. The universe isn't just a collection of individual galaxies evolving in isolation. It's an interconnected ecosystem where every component influences every other component in subtle but profound ways. The temporary nature of these dormant phases raises intriguing questions about galactic memory. Do galaxies somehow remember their previous active periods and use that information to guide their future evolution? There's growing evidence that the structure and composition of a galaxy's stellar population carries information about its formation history, like rings in a tree trunk that record years of growth and stress. By studying the ages and chemical compositions of stars in these sleeping beauty galaxies, astronomers can begin to reconstruct their complex histories of activity and rest. What makes this detective work particularly challenging is that stellar populations from different burst periods can become mixed together over time, like ingredients in a cosmic soup that has been stirred for millions of years. Separating out the individual components requires sophisticated analysis techniques that can identify subtle differences in stellar ages and chemical compositions. But when successful, these studies reveal the rhythm of galactic evolution in unprecedented detail. The discovery has also highlighted the incredible sensitivity of star formation to small changes in conditions. The difference between an active star-forming galaxy and a dormant one might come down to relatively minor shifts in gas temperature, pressure, or turbulence. It's a reminder that despite their enormous size and mass, galaxies are surprisingly delicate systems that can be dramatically affected by seemingly small perturbations. This sensitivity has profound implications for our understanding of galaxy formation in the early universe. If small changes can have such dramatic effects, then the diversity of galaxy types we observe today might reflect the cumulative impact of countless minor variations in initial conditions, environmental factors, and evolutionary histories. It's like how small differences in weather patterns can lead to completely different ecological outcomes over time. The Sleeping Beauty phenomenon also provides new insights into the relationship between galaxy mass and star formation efficiency. We've long known that more massive galaxies tend to be less efficient at forming stars relative to their total mass. But the discovery of dormant galaxies across a wide range of masses suggests that this relationship is more complex and dynamic than we thought. Even relatively small galaxies can experience periods of complete shutdown, while some massive ones maintain steady activity. This mass independence of dormancy suggests that the underlying physical processes are quite universal, operating across a wide range of galactic environments and scales. It's not just massive galaxies with powerful black holes that can shut down their star formation. Even modest systems can find ways to temporarily halt their stellar production lines. This universality points to fundamental physical principles that govern star formation across all scales of cosmic structure. The timing of these dormant phases also provides clues about the broader evolution of the universe. The fact that we observe these sleeping beauties primarily in the early universe suggests that the conditions that allow for such dramatic shutdown events were more common in the past as the universe has aged and evolved. The cosmic environment has changed in ways that make these extreme dormancy events less likely to occur. This temporal evolution reflects the changing balance between the various physical processes that govern galaxy formation in the early universe, when gas densities were higher and the cosmic web was more dynamic. The conditions were ripe for the kind of dramatic feedback events that could shut down entire galaxies. But as the universe expanded and cooled, these extreme events became less common, leading to the more steady patterns of star formation we observe in nearby galaxies today. The discovery of sleeping beauty galaxies represents more than just an interesting astronomical curiosity. It's a window into the fundamental processes that shaped our universe and continue to influence cosmic evolution today. By understanding how and why these ancient galaxies could take such dramatic breaks from star formation, we gain insights into the delicate balance of forces that determine whether galaxies thrive or struggle, whether they grow steadily or in fits and starts. As we prepare to explore how these cosmic sleeping beauties might eventually wake up and what their dreams might tell us about the future of star formation, we're reminded that the universe is far more dynamic and surprising than we ever imagined. These dormant galaxies aren't just taking a rest, they're part of a grand cosmic symphony, where periods of activity and quiet combine to create the rich, diverse universe we inhabit today. And as we drift deeper into this cosmic mystery, we encounter one of the most remarkable examples of these sleeping beauties, a galaxy that astronomers have dubbed Pablo's Galaxy. A celestial structure so extraordinary it reads like something from a science fiction novel. Here we have a galaxy caught in the very act of being put to sleep by its own central black hole, like a cosmic lullaby sung by the most powerful force in the universe. Pablo's galaxy sits roughly 13 billion light-years from Earth, meaning we're seeing it as it existed when the universe was barely 700 million years old, a cosmic infant by any measure. Yet this young galaxy had already grown massive enough to host a supermassive black hole, millions of times more massive than our Sun. But this wasn't just any ordinary black hole quietly sitting at the galaxy's center. This was an active monster feeding voraciously on surrounding matter, and in the process creating one of the most spectacular displays of cosmic power ever observed. What makes Pablo's galaxy so extraordinary isn't just the presence of this feeding black hole, it's what that black hole is doing to its host galaxy. As matter spirals into the black hole, it doesn't simply vanish. Instead, it creates a cosmic hurricane of energy that manifests as powerful jets, streams of charged particles moving at nearly the speed of light. These jets don't just gently nudge the surrounding gas, they blast it away with the fury of a cosmic gale-force wind, moving at speeds of over 1,000 kilometers per second. Imagine, if you will, trying to fill a bathtub while someone stands beside you with a fire hose pointed directly at the drain. That's essentially what's happening in Pablo's galaxy. The galaxy is trying to accumulate gas from its surroundings to fuel new star formation, but the central black hole is simultaneously blasting away that very same gas faster than it can be replenished. It's a cosmic tug-of-war between the galaxy's gravitational appetite and the black hole's explosive rejection of material. The sheer scale of this gas ejection is mind-boggling. The black hole is expelling material at a rate that far exceeds what the galaxy needs to maintain healthy star formation. It's not just preventing new stars from forming, it's actively stripping away the galaxy's ability to ever resume normal stellar production. It's like a cosmic vandal that doesn't just turn off the lights, but rips out all the electrical wiring, ensuring the building stays dark. But Pablo's galaxy isn't unique in this regard. It's simply the most dramatic example we've found of a phenomenon that appears to be relatively common in the early universe. The James Webb Space Telescope has now identified multiple galaxies where supermassive black holes appear to be actively shutting down star formation through these powerful outflows. It's a process that astronomers call feedback, but that hardly captures the violence and drama of what's actually occurring. The physics behind this process are as elegant as they are destructive when matter falls toward a black hole. It doesn't plunge directly in. Instead, it forms a swirling disk of superheated material that glows brighter than billions of stars. This accretion disk becomes a natural particle accelerator using magnetic fields to launch jets of material along the black hole's rotation axis. These jets can extend for hundreds of thousands of light years beyond the galaxy itself, creating vast cavities in the surrounding gas. What's particularly fascinating is how this process can be self-regulating. As the black hole feeds more vigorously, it produces more powerful jets, which clear away more gas, which reduces the amount of material available for the black hole to consume. Eventually, the black hole's food supply dwindles, the jets weaken, and gas can begin to fall back toward the galaxy center, potentially restarting the entire cycle. It's like a cosmic thermostat that automatically adjusts the galaxy's star formation rate. This self-regulation helps explain why the dormant phases in Sleeping Beauty galaxies appear to be temporary rather than permanent. The black hole doesn't permanently destroy the galaxy's gas supply. It simply makes it temporarily unavailable for star formation. Over millions of years, the expelled gas can cool down and gradually fall back toward the galaxy, or new gas can be accreted from the surrounding cosmic web, slowly refilling the galaxy's stellar fuel tanks. The discovery of galaxies like Pablo's has revolutionized our understanding of the relationship between supermassive black holes and their host galaxies. We used to think of black holes as parasites that simply consume their host's resources without giving anything back, but now we see them as cosmic gardeners that can prune their galaxies, keeping them from growing too quickly or becoming too massive. It's a symbiotic relationship where the black hole's destructive power actually serves a constructive evolutionary purpose. This relationship becomes even more intriguing when we consider the timing of these events. The supermassive black holes in Sleeping Beauty galaxies appear to become active at precisely the moments when their host galaxies are undergoing rapid growth phases. It's as if the black holes can sense when their galaxies are getting too enthusiastic about star formation and step in to apply the cosmic brakes before things get out of hand. The mechanism by which black holes detect and respond to their galaxy's activity is still something of a mystery, but it likely involves the complex interplay between the galaxy's gas supply, the black hole's accretion rate, and the feedback effects of the jets themselves. When a galaxy begins forming stars rapidly, it produces more gas that can potentially feed the central black hole. This increased feeding rate makes the black hole more active, which strengthens its jets, which more effectively clears away the star-forming gas. What emerges is a picture of galaxies as self-regulating systems that maintain a delicate balance between growth and restraint, like cosmic organisms that have evolved sophisticated mechanisms to prevent themselves from consuming their resources. Too quickly, the black hole acts as a kind of cosmic brake system that prevents runaway star formation, ensuring the galaxy doesn't exhaust its fuel supply too rapidly. This regulatory mechanism also helps explain one of the great mysteries of galaxy evolution. Why don't all galaxies convert all of their available gas into stars as efficiently as possible from a purely gravitational perspective? There's no reason why galaxies shouldn't be incredibly efficient star-forming machines. But observations show that most galaxies convert only a small fraction of their available gas into stars, with the rest remaining in an unusable form. The answer appears to lie in these feedback processes. The combination of stellar winds, supernovae explosions, and black hole outflows creates a complex web of energy injection that heats and disperses the galaxy's gas supply, making it much more difficult for stars to form. It's like trying to build a sandcastle while someone keeps shaking the sand. The raw materials are there, but the conditions make construction nearly impossible. What's particularly remarkable about the Sleeping Beauty phenomenon is how it reveals the interconnected nature of galactic ecosystems, a change in one component. Whether it's the central black hole, the stellar population, or the gas supply, can cascade through the entire system, causing dramatic shifts in the galaxy's behavior. It's a reminder that galaxies aren't just collections of stars and gas. They're complex dynamic systems with their own internal logic and evolutionary pressures. The study of these dormant galaxies has also revealed surprising diversity in how different systems respond to similar physical processes. Some galaxies shut down completely for millions of years, while others experience more modest reductions in star formation rates. Some appear to cycle regularly between active and dormant phases, while others seem to experience random, sporadic shutdowns. This diversity suggests that the detailed history and environment of each galaxy plays a crucial role in determining its evolutionary path. The environmental context of these sleeping beauties adds another layer of complexity to the story. Galaxies don't evolve in isolation. They're embedded in a vast cosmic web of dark matter filaments that channel gas and smaller galaxies toward larger structures. The rate at which a galaxy can acquire new gas depends critically on its position within this web and the properties of its cosmic neighborhood. Galaxies located at the intersections of multiple dark matter filaments have access to steady streams of fresh gas that can help them recover from dormant phases more quickly, while those in more isolated regions might remain quiet for much longer periods. It's like the difference between a restaurant located at a busy intersection versus one tucked away on a quiet side street. The location dramatically affects the flow of customers, or in this case, cosmic fuel. The discovery of sleeping beauty galaxies has also provided new insights into the formation of the first supermassive black holes in the universe. These cosmic monsters had to grow from much smaller seeds, potentially stellar mass black holes left behind by the first generation of stars, but growing from 10 solar masses to 10 million solar masses in less than 1 billion years requires sustained periods of rapid feeding. The fact that we observe active supermassive black holes in galaxies that are barely 700 million years old suggests that these black holes must have experienced periods of extremely efficient growth. But the same feeding process that allows rapid black hole growth also produces the powerful jets that can shut down star formation in the host galaxy. It's a delicate balance between feeding the monster and preserving the galaxy. This tension between black hole growth and galaxy evolution has profound implications for our understanding of cosmic history. The most massive black holes we observe today had to achieve most of their growth during these early epochs, when the universe was dense with gas and the conditions were right for rapid accretion. But this same period was also when galaxies were trying to build up their stellar populations through intense star formation. The result is a complex dance between competing processes, where black holes and galaxies alternately cooperate and compete for the same limited gas supply. Sometimes the galaxy wins and experiences a burst of star formation that adds significantly to its stellar mass. Other times the black hole wins and clears away the gas, leaving the galaxy dormant, but able to grow through accretion of new material from its surroundings. This cosmic competition helps explain why the relationship between black hole mass and galaxy mass appears to be so tightly regulated in the local universe. Despite billions of years of complex evolution, the ratio of black hole mass to galaxy mass remains remarkably consistent across different types of galaxies, suggesting some fundamental regulatory mechanism. The Sleeping Beauty galaxies provide a window into how this regulation might work in practice, by periodically shutting down star formation. Black holes prevent their host galaxies from growing too rapidly, while the temporary nature of these shutdowns ensures that galaxies don't remain permanently quenched. Instead, they experience a series of growth spurts separated by rest periods that allow the system to maintain its overall balance. What makes this regulatory mechanism particularly elegant is how it automatically adjusts to the galaxy's mass and environment. More massive galaxies have more powerful black holes that can more effectively shut down star formation, but they also have stronger gravitational fields that can more easily retain their gas supply. The result is a self-tuning system where the strength of the regulatory mechanism scales with the galaxy's ability to resist it. As we continue to study these remarkable cosmic sleeping beauties, we're beginning to understand that dormancy isn't a failure of galaxy evolution. It's a feature, a sophisticated mechanism that allows galaxies to pace their growth, optimize their star formation efficiency, and maintain the delicate balance between different components of their internal ecosystem, like cosmic creatures that have learned the value of rest. These galaxies use their quiet periods to prepare for future bursts of activity. The discovery of Sleeping Beauty galaxies has opened an entirely new chapter in our understanding of cosmic evolution. But perhaps the most intriguing aspect of this phenomenon is what it tells us about the future awakening of these dormant giants, like cosmic alarm clocks set to ring at some distant hour. These galaxies carry within them the seeds of their own revival, waiting for the right conditions to stir from their million-year slumbers and resume their stellar symphonies. The process by which a sleeping beauty galaxy might wake up is as fascinating as the mechanisms that put it to sleep in the first place. Imagine a cosmic ecosystem slowly healing itself after a period of upheaval. The gas that was once blasted away by powerful black hole jets doesn't simply vanish into the void. Instead, it forms vast halos of hot material surrounding the galaxy, like cosmic cocoons that gradually cool and settle over millions of years. This cooling process is remarkably similar to how a cup of tea gradually returns to room temperature, but on scales so vast that the entire solar system would be lost in the steam as the expelled gas cools. It begins to lose the energy that was keeping it dispersed, and gravity, the patient sculptor of the cosmos, starts to pull it back toward the galaxy's center. It's a gentle process, at first like the first drops of morning dew forming on leaves, but gradually it accelerates as more and more material begins its long journey home. What makes this cosmic homecoming particularly beautiful is how it mirrors the natural cycles we see everywhere in nature, just as forests regrow after fires and ecosystems recover after disturbances. Galaxies, too, have their own seasons of destruction and renewal. The gas that returns to a previously dormant galaxy often brings with it new elements and energy acquired during its cosmic wandering, creating conditions that might be even more favourable for star formation than before. The timing of these awakenings appears to follow its own mysterious rhythm. Some sleeping beauty galaxies might doze for just 10 million years, a brief nap in cosmic terms before stirring back to life. Others might slumber for 100 million years or more, like cosmic Rip Van Winkles, who wake to find the universe subtly changed around them. But the remarkable thing is that they do wake up. These dormant phases are not permanent deaths, but temporary pauses in the grand symphony of stellar creation. When a sleeping beauty galaxy does begin to stir, the process often starts slowly at first. Just a few molecular clouds here and there begin to collapse under their own gravity, forming small clusters of modest stars like cosmic embers beginning to glow in a fireplace that has been cold for too long. But as more gas becomes available and conditions improve, the process accelerates, leading to what astronomers call a starburst phase, where the galaxy suddenly blazes back to life with renewed vigour. These reawakening events can be absolutely spectacular, transforming a quiet, dormant galaxy into one of the most luminous objects in its cosmic neighbourhood. The newly formed stars burn bright and hot, illuminating vast clouds of gas and dust that had been invisible during the dormant phase. It's like watching a dark theatre suddenly flood with light as the curtain rises on a cosmic performance that has been years in the making. But the awakening of sleeping beauty galaxies isn't just a local event. It has profound implications for the broader cosmic environment. The intense radiation from newly formed stars can ionize surrounding gas, creating bubbles of hot plasma that expand outward, affecting neighboring galaxies and the intergalactic medium. It's a reminder that in the cosmic web, everything is connected, and the awakening of one galaxy can trigger changes that ripple outward across vast distances. The chemical signature of these reawakening events is particularly fascinating during their dormant phases. Galaxies continue to evolve chemically as their existing stars age and die, enriching the interstellar medium with heavy elements. When star formation resumes, the new generation of stars incorporates these elements, creating stellar populations that are chemically distinct from those formed before the dormant period. It's like being able to read the galaxy's diary written in the chemical compositions of its stars. This chemical archaeology allows astronomers to reconstruct the complex histories of sleeping beauty galaxies, identifying not just when they went dormant, but also when they woke up and how vigorous their subsequent star formation was. It's detective work on a cosmic scale where the clues are written in starlight and the story spans hundreds of millions of years. The role of external triggers in galaxy awakening adds another layer of complexity to this cosmic narrative. While some galaxies might wake up naturally as their expelled gas cools and returns, others might be roused by external events. A close encounter with a neighbouring galaxy can compress gas clouds, triggering renewed star formation, or the infall of a smaller satellite galaxy can provide fresh fuel for stellar creation. It's like having multiple alarm clocks set at different times, ensuring that even the deepest cosmic sleepers eventually stir. What's particularly intriguing is how the awakening process might be influenced by the galaxy's previous history galaxies that have experienced multiple cycles of dormancy. And reawakening might develop a kind of cosmic memory encoded in the structure of their stellar populations and gas distribution. This memory could influence how readily they respond to awakening triggers and how vigorous their subsequent star formation becomes. The study of galaxy reawakening has also revealed the importance of cosmic timing. The same external trigger that might cause a vigorous starburst in a galaxy that has been dormant for 50 million years might have little effect on one that has only been quiet for 10 million years. It's as if galaxies need a certain amount of rest before they're ready to resume full activity, like cosmic athletes who need adequate recovery time between training sessions. This timing sensitivity helps explain the diversity we observe in galaxy populations across the universe. Galaxies that happen to be awakened early in their dormant phases might experience modest increases in star formation, while those that are allowed to rest for longer periods might undergo dramatic starbursts when finally roused. The result is a rich tapestry of galactic behaviours that reflects the complex interplay between internal evolution and external influences. The awakening of sleeping beauty galaxies also provides insights into the future evolution of our own cosmic neighbourhood. While the Milky Way doesn't appear to be currently dormant, it has likely experienced its own cycles of activity and rest throughout its long history. Understanding how other galaxies wake from dormancy might help us predict how our own galaxy will evolve as it continues to interact with its neighbours and accrete material from the surrounding cosmic web. Perhaps most remarkably, the study of these cosmic awakenings has revealed that dormancy might actually improve a galaxy's long-term prospects for star formation. During quiet periods, the galaxy's gas can settle into more organised structures, turbulence can dissipate, and conditions can become more favourable for efficient star formation when activity resumes. It's like allowing a busy kitchen to reorganise between service periods, ensuring that the next meal preparation goes more smoothly. This optimization effect might explain why some of the most prolific star-forming galaxies in the universe appear to have histories that include dormant phases rather than hindering their evolution. These quiet periods might have allowed them to fine-tune their internal structure and prepare for more efficient star formation in the future. It's a reminder that sometimes the best way forward is to pause, take stock, and prepare for what comes next. The discovery that dormancy can actually enhance rather than hinder galaxy evolution has profound implications for our understanding of cosmic efficiency. We used to think that the most successful galaxies would be those that never stopped forming stars that maintained constant activity throughout their histories. But the Sleeping Beauty phenomenon suggests that strategic pauses might be a key component of optimal galactic evolution. This insight extends beyond astronomy into broader questions about growth and development in complex systems. Whether we're talking about ecosystems, businesses, or even personal development, there appears to be wisdom in the cosmic rhythm of activity and rest periods of intense growth, balanced by times of consolidation and preparation. It's a lesson written in starlight that resonates across scales from the smallest bacterial colony to the largest galaxy. The role of cosmic environment in determining awakening patterns adds yet another dimension to this story. Galaxies in dense cosmic neighborhoods with many nearby companions might experience more frequent awakening triggers as gravitational interactions stir up their gas reservoirs, while those in more isolated regions might have longer, more regular cycles of dormancy and reawakening. It's like the difference between living in a busy city where there's always something happening and residing in a quiet countryside where change comes more slowly but perhaps more peacefully. What emerges from all this complexity is a picture of the universe as a vast interconnected ecosystem where galaxies like living organisms go through natural cycles of growth, rest, and renewal. The Sleeping Beauty phenomenon isn't an anomaly or a failure of cosmic evolution. It's a fundamental feature of how complex systems manage their resources and optimize their long-term survival strategies. As we peer deeper into space and further back in time with increasingly sophisticated instruments like the James Webb Space Telescope, we're likely to discover even more examples of these cosmic sleeping beauties, each one adding another piece to the puzzle of how galaxies grow, evolve, and thrive in the ever-changing cosmic environment. And perhaps most wonderfully, each discovery reminds us that the universe is far more dynamic, creative, and surprising than we ever dared imagine. The Sleeping Beauty galaxies teach us that even in the vastness of space, patience can be a virtue, that rest can be productive, and that the most beautiful cosmic performances often follow periods of quiet preparation. They remind us that the universe has its own rhythms, its own seasons of activity and dormancy, and that by listening carefully to these cosmic heartbeats, we can begin to understand the deeper patterns that govern the evolution of everything we see. As our journey through this cosmic mystery draws toward its gentle conclusion, we are left with a profound sense of wonder at the intricate dance of creation and rest that plays out on scales so vast they dwarf our everyday experience. Yet somehow these distant sleeping beauties speak to something fundamental about the nature of growth, change, and renewal that resonates even in our small corner of the cosmic web. And so we find ourselves witnesses to one of the most beautiful discoveries in modern astronomy. The revelation that even galaxies, those island universes that seem so permanent and unchanging, have their own dreams, their own seasons of sleep and awakening, their own stories of rest and renewal, written across the cosmic dark in letters of starlight. And perhaps most beautifully, the Sleeping Beauty galaxies offer us a mirror into our own cosmic future. As we contemplate these distant, dormant giants, we're not just looking backward through time to the universe's youth, we're glimpsing patterns and processes that continue to shape the cosmos today, including the very galaxy we call home. Our own Milky Way, that grand spiral of stars and gas that cradles our solar system, bears the subtle scars and signatures of its own complex history. While it may not currently be experiencing the dramatic dormancy we see in these ancient sleeping beauties, astronomical detective work suggests it too has known periods of relative quiet, punctuated by bursts of intense stellar activity. The chemical compositions of stars in our galactic neighborhood tell stories of ancient starbursts and lulls, like chapters in a cosmic autobiography written in the language of heavy elements. What's particularly fascinating is how this discovery reshapes our understanding of galactic citizenship. We're not just passengers aboard a steadily churning star-making machine, we're residents of a dynamic, breathing entity that has its own moods, its own cycles, its own capacity for both dramatic change and peaceful reflection. The very elements that make up our bodies, the carbon in our cells, the iron in our blood, the oxygen we breathe, were forged in stellar furnaces during previous episodes of galactic activity, then scattered into space during periods of stellar death and rebirth. The implications ripple outward into our understanding of life itself. If galaxies experience these cycles of dormancy and awakening, then the conditions for life across the universe are far more variable and complex than we once imagined. There might be cosmic seasons when entire regions of galaxies become inhospitable to planet formation, followed by golden ages when conditions are perfect for the emergence of solar systems like our own. This cyclical view of galactic evolution also offers a more nuanced perspective on the search for life beyond Earth. Rather than assuming that star formation and planet formation proceed at steady, predictable rates throughout cosmic history, we now understand that there are natural rhythms to cosmic creativity. Some epochs might be particularly fertile for the emergence of life-bearing worlds, while others might be dominated by the cosmic equivalent of winter, necessary periods of rest that set the stage for future springs of stellar birth. The Sleeping Beauty phenomenon has also revealed something profound about the nature of cosmic time itself. When we speak of a galaxy being dormant for 25 million years, we're talking about a period that spans the entire evolutionary history of many species on Earth. Yet in the context of galactic evolution, this is merely a brief pause, a cosmic catnap that barely registers on the timeline of stellar creation. It's a humbling reminder of the vastly different scales on which the universe operates, where our entire recorded history is but a fleeting moment in the long story of cosmic development. This perspective on cosmic time offers a strange kind of comfort. The universe, in all its vastness and complexity, operates according to rhythms and patterns that suggest a deep underlying order. Galaxies don't just randomly stop and start their stellar factories. They follow natural cycles that emerge from the interplay of fundamental physical processes. There's something almost musical about these cosmic rhythms, like a vast symphony where individual movements of activity and rest combine to create a larger harmony. The study of sleeping beauty galaxies has also highlighted the remarkable resilience of cosmic structures. Despite experiencing dramatic shutdowns that clear away their star-forming fuel, these galaxies don't simply fade into obscurity. Instead, they demonstrate an almost organic capacity for recovery and renewal. They're like cosmic forests that can regenerate after fires, or ecosystems that can bounce back from disturbances, suggesting that the universe has built-in mechanisms for healing and self-renewal. This resilience extends to the very process of awakening itself. As these dormant giants begin to stir from their slumber, they often do so with renewed vigor, creating some of the most spectacular displays of star formation ever observed. It's as if the period of rest has allowed them to reorganize their internal structure, optimize their star-forming processes, and prepare for even more magnificent creative outbursts than they experienced before their dormancy. The awakening process also reveals the deeply interconnected nature of cosmic evolution. When a sleeping beauty galaxy begins to form stars again, the energy and matter it releases doesn't stay confined within its own boundaries. Instead, it spreads outward, affecting the surrounding cosmic environment and potentially triggering changes in neighboring galaxies. It's a reminder that the universe is not a collection of isolated objects, but a vast web of relationships where every event has consequences that ripple outward across space and time. Perhaps most wonderfully, these discoveries remind us that the universe is still writing its story. The sleeping beauty galaxies we observe today are not museum pieces frozen in time, but active participants in an ongoing cosmic drama. Some of them are still dreaming their deep dreams, while others may be on the verge of awakening to begin new chapters of stellar creation. We are witnessing not just the history of the universe, but its continuing evolution, its ongoing creativity, its endless capacity for surprise and renewal. The James Webb Space Telescope, with its unprecedented ability to peer into the infrared depths of space, has given us ringside seats to this cosmic theatre. But more than that, it has shown us that we are not just observers, but participants in this grand story. The very atoms that make up our bodies, our planet, our solar system are all products of the same processes we see playing out in these distant galaxies. The cycles of stellar birth and death, the complex interplay of gravity and energy, the endless dance of creation and renewal that defines the cosmos. As we continue to study these remarkable sleeping beauty galaxies, we're likely to uncover even more surprises about the nature of cosmic evolution. Each new observation adds another piece to the puzzle, another verse to the cosmic song, another brushstroke to the vast canvas of space and time. And through it all, we're reminded that we live in a universe that is far more dynamic, creative, and beautiful than we ever dared imagine. The sleeping beauties teach us that even in the apparent emptiness of space, even in the seeming silence of dormant galaxies, there is activity and potential and promise. They remind us that rest is not the absence of creativity, but a different kind of creativity, a gathering of resources and energy in preparation for future flowering. They show us that the universe has its own wisdom about timing and rhythm, about when to act and when to wait, about the delicate balance between effort and repose. So tonight, as you settle into your own rest beneath the same stars that shine down on these distant sleeping beauties, remember that you are part of this cosmic story. Your dreams and theirs are woven from the same fundamental threads: matter and energy, time and space, the endless interplay of forces that shapes everything, from the smallest atom to the largest galaxy. In your quiet moments, you share something profound with these dormant giants. The recognition that sometimes the most important thing you can do is simply pause, gather your resources, and prepare for whatever cosmic dawn awaits. And perhaps in some distant future, when our own galaxy experiences its next great awakening, when new generations of stars blaze forth in spectacular abundance, some of that light will carry with it the memory of this moment, when curious minds on a small planet orbited around an ordinary star took time to contemplate the beautiful mysteries of sleeping galaxies, and found in them reflections of their own capacity for rest, renewal, and wonder. The universe sleeps, and the universe dreams, and in those dreams lie the seeds of all the stars yet to be born. Sweet dreams, fellow travellers. May your rest be as profound as a sleeping galaxies, and may your awakening be as brilliant as the birth of new stars. As the birth of new stars.